Okay, it's time to begin. So that's what I'll do. Today's the first lab. So for the first lab, there's obviously a lot of learning. The purpose of today's lab is simply to learn how to make some basic measurements. We're going to be making measurements both for timing things as well as for measuring size. Reminds me I need to log in on this computer if I'm going to show you how to do that. So we're going to use the laptops for timers. If you have a timer like on your smartphone that measures out to 1/1000th of a second, you can use that. But if it only measures to hundredths of a second, then you need to use the timers in the laptops just so we can have that additional digit. So to get started, everybody hopefully now has the lab guide. And we're going to work in groups of 2. So you'll want to find your best friend that you think will get you through this quickly when it gets that time. And we're going to learn a little bit about making measurements. So I have here in the lab guide a little preamble that talks about measurements and stuff and points out that no measurement is perfect. Things like I talk about how old you are. And I can make an estimate that you all are 19 years plus or minus 2. That's probably a reasonably good estimate for your age. There could be an older student, there could be a younger student. I know I had a 15-year-old classmate when I started college. But it's a good estimate. But that has an uncertainty, that plus or minus 2 years. When I say 19 years plus or minus 2 years, that's covering from 17 to 21. Now, we could try to be more exact. So we could, look at, okay, so what year were you born? I was born in 1966. And so you say, okay, born in 1966, well then that means you must be somewhere between what ages? Between 49 to 50. I thought I heard 59, that was my. Not that old. Old, but not that old. So you can say, okay, so I must be somewhere between 49 and 50. So you can narrow it down to 2 years. And then I can go further and say, well, I was born November 13, 1966. Well, then you can get it down to the day. But there's still an uncertainty in my age, right? You don't know if I was born at midnight, which part of the day. So there's still the hours and minutes. It's still plus or minus, at least half a day on my age. You could go further. You could look at my birth certificate and see what time it says I was born. But even then, how do you define the time when a child is born? Is it the time when the head first crowns, or is it the time when the whole baby comes out? That you can never get exact values. And so one of the things in science is whenever we make a measurement, it's important that we specify how precise are we? That is, okay, there are 2 words here, precise and accurate. What's the difference in precision and accuracy? Anybody? Okay, there's a very simple example of, okay, I don't have lots of empty space on these like I do on other things, but if you're like shooting at targets, and so you have a target, and if you shoot away, and you shoot, here's one, 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 those are very reproducible. And so we would say that that is very precise. So precision is being very reproducible, being very, you measure to 10 decimal places. That's more precise than measuring to 5 decimal places. But what's wrong with my shooting pattern there? It's not accurate. It's not close to the bullseye. So I could have an alternate version where my shots go something like one here, one here, one here, one here, one here, one here. Now in this case, if you take the average of all of those shots, it's pretty close to hitting the bullseye. So we would say that that was reasonably accurate, but not very precise. And of course, your goal, if you're a competitive shooter, is going to be both accurate and precise. That is to have a tight cluster around the center of the target. So when we're making measurements, precision, of course, is how reproducible something is. But you can have something that's very reproducible, but that's not right. You know, you could use the instrument wrong or something like that and have a constant offset, and so it'd be inaccurate but precise. So when we're looking at measurements, we try to identify anything that could make us inaccurate or precise, and then have an estimate of just how far off we probably are. So for our measurements, or for the actual lab experience, we're going to start by making measurements. Now, I'm going to, in my description, go through making measurements of length first. In the actual lab, it has you doing time first. Here I noticed that when I printed it, the PDF I made did not have all the detail that the picture, right, what you see here and what you see there, it doesn't have the same detail. I don't know why, because I just printed this with the same thing and it comes out here with that. Anyway, if we're measuring with a meter stick, and our meter stick, we're measuring in meters, centimeters. So this is A6.5 centimeters, A6.6 centimeters. If this is A6.5 and this is A6.6, what is the value where this edge crosses? What can you say with 100% certainty? Go ahead, Daisy. Okay. That would be your estimate, but I wanted to back up away from that with what you can say with exact certainty. Right, that there is, yeah. What you can say with exact certainty is this between 86.5 and 86.6. And then you have to estimate how far it is between those two. So you look at those, and it's a little bit more than halfway. And so I say, well, a little bit more than halfway, I'm estimating, let me say that's 6/10 of the way. And so I say it's 86.5 plus 6/10 of the next digit. So I put, or 6/10 for the next digit. So I put 6/10 times 0.1 because it's 6/10 of a tenth being the last digit it shows. And so then when I add those together, that's 86.5 plus 0.06, so 86.56. Now a redundant question, but what I want you to answer anyway. Is that exactly correct? No. Why not? Because what? Can't get an exact measurement, and in fact, I estimated, didn't I? That's something we always do when we make measurements. We actually have to think and estimate. We can't just get a blind answer. So I had to estimate this digit, so I'm going to now have to specify how much could I have been off in my estimate for that digit. So I look at this, looking at the size and judging my perceptions of space. If I was really, really optimistic, I'd say, I'm probably within, 0.01 there, 1 in that digit I estimated. That's pretty optimistic. That would be, if I said 1 digit, that'd be between A6.55 and A6.57. A little more, giving myself room to not be perfect, would say, plus or minus 2 in that digit. Now, what I wrote here is I usually say, well, I know for sure that I'm going to be able to judge plus or minus 1/4 of my spacing. I mean, I'm really confident in that. And rounding to 1 digit, 1/4 is 0.3. And so I use as my standard 3 for that estimate if it's based on my best ability to gauge how much it is between. But you could go with 2, right? It's your estimate of how much confidence you have. And so I have here 86.56 plus or minus. The plus or minus means it could be going up or going down, 0.03. Now, things to note, because I estimated the last digit, my uncertainty is in that last digit, in the one I estimated. I don't have my uncertainty in, we call it the tenths, in the tenths digit, because I didn't estimate that one. I knew that one for sure. It's in the one I estimated. So anytime you're doing your uncertainty should be in the digit you estimated. So if I use something like a meter stick to make measurements, the meter stick is marked off in centimeters, 40 centimeters, 50 centimeters, 41, 42, 43, and then it has smaller lines, which are tenths of a centimeter, which means a millimeter. So this is marked off in millimeters. So if I estimate, what digit am I estimating? The millimeters I can read directly, because I can see it's between this one and that one. Tenth of a millimeter. Then I'm going to be estimating the tenths of a millimeter. And so my uncertainty needs to be in that tenth of a millimeter. And when you look at the spaces here, my 3 in that digit I estimated makes a lot more sense. Right? There was a nice, big, easy to read difference there. When you're measuring on this, you don't have that nice, big, easy to read separation. And so plus or minus of, if I'm doing it in centimeters, I could read, 86.5 centimeters directly, and then I would be estimating the next digit, and I would definitely have 3 in that digit if I'm using the meter stick. Now the meter stick has some other issues. The ends of the meter stick, I will go to my Bronco friend. What would you tell me about the quality of the end of that meter stick?
It's not very good.
It's not very good. It's all kinds of beat up. If you take this and measure from the ground up to here and say, oh, that's exactly 1 meter, you're wrong. Because the ends of these are often not even calibrated. Many times you can actually see the mark, that's the 0 mark, on the wood. Right? So the 0 mark starts in on the wood, not at the end. So you should never use the ends of a meter stick for measuring, because those aren't calibrated. Now, if you look at the rulers, there are actually only 3 of these. I ordered 4 packets of 5, and they sent me 4 singles. And so yeah, that's why there's like 3 of these. These here, they made a nice rounded edge that sticks out here well away from 0, so nobody's going to try to use the end of the ruler as if that's where 0 is. Right, so that's one of the things you have to do. Make sure you know where 0 is. When you're using something like a meter stick, I usually start at 10 centimeters because that's well marked. And then I just have to remember to subtract 10 at the end. So when you're measuring, when you're measuring, you have to also keep in mind what kinds of problems there might be with your instrument, not just with your estimating. Now we're going to measure distances. Specifically, we're going to measure the diameter of a little ball bearing. If I put this ball bearing on my meter stick and try to measure the diameter, what kind of things am I going to have to deal with?
Well, it's rounded, so you can't really tell.
Yeah, it's rounded. How are you going to measure the edge when it's rounded? Of course, there are ways to get around that. How can you get around that? That is the one I'm looking for. Don't think that I'm saying, oh no. That's exactly what I'm looking for. How can I try to improve the uncertainty that would cause?
Can you line up like 2 straight edges on either side of it?
She's all over this. That is exactly what you would do, yeah. Take something that has a right angle slide it up on either side, and then you can read where those are, and you know where the edges are. If you just put it like this, you have the problem that we call parallax. If I look at an angle like this, I'll see the edge actually underneath it. If I look at an angle like this, I'll see the edge, well, like that, outside of it. And so it just depends on where your head is, where it's going to look like the edge is. Well, that's no way to make a measurement. But if you put something up there, then you can see where the edge is and get an accurate measurement. Or you can use something like this. These here are called calipers. This instrument is called a vernier caliper because it has a special scale. I'll show you how to use that scale in just a moment. So you're going to use one of these to measure the diameter of your ball, as well as using that to measure the diameter. So how do you use this, you ask? Well, first, notice when I close it up, there's a hole here. I can see through the hole. That means that when this is closed and it says 0, it's not a separation of 0 where the hole is. So don't put something in where that hole is and try to measure it, because you'll be measuring the wrong thing. These spaces here should be touching when it's 0. That's what we're measuring. These here, these knife edges, are for measuring inner diameters. So if you're measuring inner diameter, you use this side. Outer diameter, you use this side. So I'm going to take my ball, put it out here, tighten it up, make sure that it can slide through, and then I'll make my measurement. Now I'm going to take a picture of this so you can see what it's going to look like. I guess you won't see until after I take the picture. Another thing, I did it upside down. Okay, you can't see yet, so you won't know. Turn it this way. Okay, now you should see it, right? Oh no, you see something else, completely different. Come on. This is the way it was supposed to have been set. Somehow I got out of it. So here you can see what we call the vernier part of the vernier calipers. I have this oval here, and I have numbers. Now when you read it, the first thing you do is figure out that part that you know is absolutely correct. When you zoom in, you can see that this is not a high precision vernier caliper. Right? I did not pay top dollar for this. So this mark right here, that's your 0 marker. That is where your edge is. So if I look where that edge is, what would you say? Okay, 1.1. Now notice this here, the 1 is beside it, but the long one is the 1. And so that should be hitting at 1.1. But with this device, we don't have to estimate that last digit. We can measure one digit further. How do we do that? If you notice, going from here to here, you go from 0.1 to 2.0. That's a total of 9 spacings, right? There's 1, 2, 3. There are 9 spacings. But on the bottom, there are 10 spacings in the same distance. That's done intentionally so that there is a 10% offset. So that if they're exactly the same, as if you're at 1.10, then the first 2 lines will match up. But if you're off by 1/10 of that, if you're at 1.11, then it would be the second line that would match up and so on. So if the first one, the one that I marked as 0, matches up best with the line above it, then 0 is your next digit. if, for instance, this one matched up best with something above, you can see clearly it doesn't, then it would have been 5 was my next digit. And so I look here and I just say which one lines up the best, and I think we can probably all agree that this here is the best alignment, and so then I can read it as 1.1 I read directly, and then 0 for the last digit because that was the one that lined up. Now I'm just going to move it so you can get something that's not quite so obvious. And take another picture and do it again. Yeah. Saving the changed pages. Don't want to lose that. This application is great for most things except memory management, apparently. Okay, I'm going to actually move it a little. That's not as far away as I wanted it. Okay, so with this, what do you get for your initial reading? Notice this is 3, so that means these are 2 point somethings. So what do you get for that initial reading? Well, this here is 2.5. So I heard a 2.7, and I would agree because if this is 5, then this is 6, this is 7, and this 0, 1 is coming past the 7. So it's between 2.7 and 2.8. So I know it's 2.7, and then I have to decide what matches up best between these lines. Let me zoom in a bit. So if we look at these, which line, so 0 is marked right here, that's 1, 2, 3. Which line lines up best with the one above it? Okay, Rachel said 2. So Rachel said, this here lines up the best. Who disagrees with Rachel? No one. Usually somebody does. Because it's not a perfect matchup usually, it's really close, but you could have been off by 1 on either side, but that's the worst you could have possibly been off. That nobody's going to say, no, it's 2 over from the one you said. And so when we do this, following what Rachel gave us there, we have a value of 2.72. And then my plus or minus value, what I say was the farthest we could have been off? Just 1 in that digit, so that's 0.01. And then make sure you put your units. For any measurement, you need to have the units. If you were to just say, yes, my teacher is 189 tall, that wouldn't make a lot of sense to most people. But if you said my teacher is 189 centimeters tall, then it starts to make some sense. So you always have to put units with your numbers. So this is the way you should write measurements. Now once you have the measurement, you're doing the calculations, things get a lot more intense, and we just use what we call significant digits. If I had 3 digits in this number and I multiply it by another number, I'll just take the smaller number of digits in the 2 numbers and keep that number for my answer. Instead of doing, there's pretty sophisticated calculations for actually keeping track of how your uncertainty propagates. So that's how you use the vernier calipers to measure. Now, our lab guide has instructions for the micrometer as well. The micrometer is our most sophisticated measuring device, but to save us time, and I don't know why I'm not seeing my page here, but I should see a page here somewhere. Save us time, I'm taking out the micrometer part of the lab. Okay, So here we go. Now we're getting back to the pages that I wanted. So for our equipment, I took out the micrometer. You don't need to go look for it. What you're going to need is one ball for each pair of people, one vernier caliper for each pair of people. There should be vernier calipers in the drawers at the end of your desks, unless it's like this one here that I stole from somebody's desk. You got yours. So everybody, each group needs one of these and a meter stick. The meter sticks are against the wall, sitting on top of the power bars. Now, remember I said I'm going to go through the measurements of distance first, but in the lab, you don't need the 2 meter stick. In the lab, we're going to start with time. And so you're going to start by saying, how long do I think it's going to take for this ball to drop 1 meter? And answer that, put a time in, without dropping the ball ever. This is just based on your perception of how long you think it's going to take. Now, do I expect you to have exactly the right value? Of course not. But I do expect you to be reasonable. If you say it's going to take an hour, you will lose points, right? Because it's going to take less than an hour for it to drop 1 meter. After you put that down, you need to give your reason why you came up with that time. What was your reasoning behind it? You know, showing your thought process. Now, after you've done that, after you've come up with your time and you've written down how long you think it's going to take, then you're going to just drop it a meter a few times, not timing it, but just dropping it and saying, did that seem like a reasonable time? And then you're answering a second time the same question. How long is it going to take to drop 1 meter? But you can change your number and you give your reasons why you did or did not change the time. And then finally, you're going to say, now how accurate do I think I am after I have actually done some practice drops to get an idea? So you're going to estimate how much you could be off, your uncertainty in that timing. You put your uncertainty there in the bottom box and your thought process that came up with that uncertainty. Now that you've done all of those things, then you're ready to do your actual measurements. So to do your actual measurements, you and your partner will work together. That's why you're in groups of 2. So one partner will take the meter stick and hold. Now I told you the meter stick, using it as a meter is wrong. But for the purposes of this, it'll work for us. So one partner is going to hold the meter stick up here and hold the ball beside the meter stick so it's at the top of the meter stick. And when the other partner is ready, I say, you ready? Says yes. Without telling me, okay, 3, 2, 1, but just drop it. I drop it, and he starts the timer when it leaves my hand, stops the timer when it hits the ground. That's his measurements at the time because he's the one who started and stopped the timer. Now, how do you do that timer action, you're wondering? If you use the one in the laptops, you just open up the, I think there should be a Physics 151 shortcut. And in that, oh, not 151, you're in 111. And in the 111, you just have a timer right now because this is the first lab. Oh, shoot, I'll put a spreadsheet in there in a minute. I have the spreadsheet, just not there. So I double-clicked and the timer came up right here. The timer is super, super unsophisticated. You start it by pressing the space bar. You stop it by pressing the space bar. What will happen when I press the space bar a third time? It both resets and starts again. So you were both right. So I hit it again, it resets and starts. So all you need to do is hit it to start, hit it to stop, record the time, record all of the digits it shows, and then repeat. It doesn't take very long to do this. After you have done your set of 5 measurements here, actually I'm not sure if it says 3 or 5. 5 is better. Yeah, it says for a total of 5 trials. Then you just switch and you have your partner do it. So you have your partner do the same thing. After you've both made your measurements, well, I don't need the timer anymore. But I do need to then enter them into the spreadsheet to do some calculations. Now that spreadsheet, will show up in a second. It should be in here. Oh heck, I'll put them all in. I think I have all of these things ready. I at least worked on them. Oh wait, we don't need faculty senate feedback on collaborative. That wouldn't be good. I'm not sure about some of these. I'm just copying everything so we have it all. Okay, so now you have the spreadsheet. So you just open up the spreadsheet. And in the first tab, you just change to Lab 01 statistics. And you put in your numbers. So, say it was 1.023, 1.321, 2.548, 9.65. Okay, so you put in your numbers, whatever they are. If you have this kind of variation, you know you did a bad job, right? If you have one that took almost 10 seconds and one that took 0.012, you know that you made a few mistakes. Go back and try to figure out where your mistakes were and just put a single line through errors and do them again. Right? Don't just keep them saying, well, that's what I got. You put your numbers in and this shows you an average. Round that average to the number of decimal places you use. So since you use 3 decimal points, just round the average to 3. Don't keep the additional one. Likewise with the standard deviation, just round the standard deviation to 1 digit. So in this case, it is 3.876. So I would just say standard deviation of 4. Okay? We're just making it simple, just using 1 digit for that. So you're going to put your numbers in and get your numbers for the average and standard deviation and fill them in on the table. Do the same for your partners. By the way, this has a place for the uncertainty in the drop time. Where are you going to get that uncertainty in the drop time? We're going to compare it to the standard deviation, but that was actually, if you look at the bottom of the preceding page, you had estimated what your uncertainty in the drop time would be. So you're going to put what your estimate for the uncertainty in the drop time is there. Now you might find that your estimate wasn't very good, but you're going to put it there because that was your estimate. That's what we're trying to do, is learn how to make those estimates. Oh, I circled it here, but I had this on the screen. Sorry. Good job answering when you can't see what's up there. There. That's where you're going to put those. Okay, so you put in your average, make this your data, and this your partner's data. On your books, write on the front cover who you are so we can identify it quickly, and if you lose it, we know whose it is. And when you're doing the lab, because you could have a different partner every week, on the pages like this where you have the data for your partner, make sure you put your partner's name. So I would recommend put the partner's name here on the first page of the lab, just so it's clear. And then when you have partner's data, just put, Rachel's data. Now you have some questions to answer. These questions are questions for you to think about and give your honest answers. Next, we're going to measure length. So that's the end of the time. For the length, we're taking out the micrometer part. So you are just going to measure the diameter of this ball. I think it just says 3 times, doesn't it? Yeah. So you're going to measure the diameter of the ball with the the vernier caliper 3 times. When you do that, put it in, tighten it up, make your measurements, take it out, spin it around, open these up, put it back in, tighten it up again. Because you want to get a different dimension on this. This may not be perfectly spherical. You want to try it in different random orientations to test the reproducibility of the shape. So you will once again make your measurements using the vernier caliper and the meter stick. Your partner's measurements, the vernier caliper and the meter stick. Make sure, well actually I put here the uncertainties so you can already not be confused by what the uncertainties are for these different instruments. And then you have a few more questions to answer and you are fundamentally done. I say fundamentally done. Okay, you have one more question to answer. The conclusions. The conclusions is actually a big piece of the credit for the lab. The conclusions should say what you learned in lab. I had a student, probably 6 years ago. On the first one I put, in this laboratory activity I learned. The rest of them I didn't because I figured they will know each time that's how they start. I learned, you don't have to use those words, but I learned this. But I had one student, how was I supposed to know that it was still going to be what we learned if it didn't say that? So now I have it on each one. But your conclusions here should be what you learned in the lab. So you're going to answer things like, did this lab meet its goal? What was the goal of the lab? So what is, since you haven't started yet, what's the goal of this lab? Okay? It's measurements. We want you to understand how to make measurements and how to estimate the uncertainties and the errors in the measurements. So you should say here statements about what you learned in those areas and if you feel that you have reached the goal, the purpose of these labs, or if it fell short. And what things could have made it better. What things went horribly wrong. What things went perfectly. That's the kind of stuff you're putting there in the conclusions. When you're done, just leave your lab book here so that we can grade them for next time. Any questions? Yeah. Okay, yeah, I'll just log you on it. Yeah, go ahead and start up all of your computers here. I have 6 computers we have. 2, 4, 6, 8. Yeah, we only need 5 computers, so we're good. So start them all up and I'll log them in.
I think I need
I think I stole one of yours, eh? Stole one of yours. One of the ones I stole was yours. Okay, so groups of 2, I will work with the odd person. Is it even?
it was
2, 4.
It was on.
Yep, you're right. It's even now. Okay, then I get the day off. Nice. Yeah. True. Why the change? There's there. Yeah. I used to just tell people the password, but then when people are typing the password, I always have people who put in the password wrong, and then if you do that 3 times, it locks everyone out so no one can use it. That's the only reason I don't tell you.